Hello everyone, welcome to the fourth UEEIV Railway Talk. Today we've got an exciting topic about the elastic solutions to railway superstructures. We have three speakers that will be giving us insight into the product itself as well as experiences on the railway in real life. So hope you are excited as I am to listen about this. We have Thomas and Stefan, who are here from Getzner to discuss about the products, and Bernhard, who is our Vice President for the UEEIV, who will talk to us about his experiences as part of the Austrian Federal Railway. This should take about an hour or so, the three talks themselves, and then we will have time for questions afterwards. Over to you, Thomas.
Thank you very much, Madeleine. Welcome everybody. I will start to share my screen too. So just a second. I hope if Madeleine or Stefan, you can just tell me that it's working.
Yeah, fine.
Okay, perfect. Yeah, welcome everybody to our presentation about elasticity in superstructure. Just a second. Check that I have to start quickly with the right. Yeah. Oh. Sorry. That was the wrong. Just a second. It's the wrong slide. Now it's working, yeah? You
Looks
can.
good.
Okay,
Yeah,
perfect. Sorry, that was the wrong slide for the beginning. Once again, welcome everybody. We'll talk about elastic solutions for railway superstructure today. Our presentation will be more on a, let me say, high and not too technical level, because we know that the group today is really a mixture. We not only have infrastructure managers, we have people from signaling, we have people from rolling stock. And we said first, our intention today is really giving an overview, talking about general principles, advantages, benefits, some references and examples. And we're happy that later on Mr. Knoll from Austrian Federal Railways will make a more deeper technical insight from an operator's view, which is great, because more trustful and worthful if the operator tells about the advantages and what they have found out. So very happy that we have the chance that Mr. Knoll is doing that. My name is Thomas Gamsjäger. I'm working for Getzner since almost 13 years. I'm the Senior Vice President of the Railway Infrastructure, and we will have a switch in the presentation. Mr. Stefan, Loacker-Schöch, Product Manager and Product Developer, will take over and also present the products today. Just a few words on our company. We were founded almost 50 years ago. Our mother company is over 200 years old. We have a railway focus since the beginning. So since the, let me say, more or less 80s, we're really focused on railway business. We are situated in Western Austria, close to Switzerland and Germany, in the area of Lake Constance, quite a beautiful area. Many people are coming for holidays here, so we are lucky to work here. And as you can see, we have few locations all over the world, but they're more or less sales offices. Our production is here situated in the headquarters in Austria. We have a small production in China. As you all know, when you do public or when you're supporting public projects in China, you have to have a joint venture there. So there is a small production here, yes. And our main focus is foamed polyurethane. That's our main material. Some of the brands you might know, Silomer and Silodyne, are quite famous in the railway industry. We are the owner of those brands. We are the producers of those materials. And foam polyurethane, that's really the main material we are doing. We have some other materials, granulated products or TP, but focus is really foam polyurethane. What are our businesses? I told you our focus is railway. We are still a railway company. It's more than 50% of our business. We have other business segments too, like construction. You know, when you forgot to isolate the railway superstructure and you start to build a building, maybe you're too late, you can also wrap the building. So with construction applications, we have shielding of buildings, flanking transmissions, floor bearings, machine foundations, all kind of these applications we have there or see there. In industry, we're talking about, for example, machine bearings with polyurethane or steel springs. We have a lot of HVAC applications like heat pumps, sport industry with shoe insoles, medical applications. So industry is quite a wide basket of different applications. But today, of course, main focus is railway business. Yeah, we talked about polyurethane. We produce foam polyurethane. Why? What is the big advantage of this material? Let me say one of the biggest advantages why polyurethane is we believe and see that it's better than other materials, for example, granulated rubber or EVA, is of course the long lifetime, and even in harsh surrounding conditions. You see on the top right a picture of an under ballast mat after 30 years in superstructure in track. You even don't realize it's an under ballast mat anymore. My colleague will talk about this reference, but still that under ballast mat was not only working, it was still in the original specification. And the longevity of this material is really extraordinary. And that, of course, reduces the life cycle costs and leads to lower maintenance. And so the cost advantage or benefit is really one of the major issues there. And some of you might have asked yourself, hey, does this material really work anymore? It doesn't look good. Water and colder temperature or these harsh surrounding conditions don't have an impact on our material. Or let me say, of course, they have an impact, but it's really less. As we are doing that since 50 years, we know what's happening, and not only from calculation, we know it from real life. And polyurethane has really the advantage that water and colder temperature are not harming them and not changing the properties. That is really one of the really special things about polyurethane. Also, the vibration isolation properties are excellent. You can achieve great vibration isolation properties with this material. That's mainly because there's one unique thing about polyurethane, that it's getting softer in the defined dynamic range. Means really on the static or the calculated load of the or static load, after we go into the dynamic, when, let me say, a train passes, the material is getting softer. And that gives an extraordinary vibration isolation, because other materials really have a progressive loading line, and that leads to this excellent vibration isolation. Means in real life, protection of surrounding infrastructure, buildings, bridges, tunnels, all the infrastructure you want to protect. And the bedding and the protection of the ballasts, the elastic plastic behavior of the material, that's also a very special thing. It's still stiff, but soft enough to embed the ballast. These stones, we always want them not to deteriorate. And that's one big advantage, that the bedding and protection of the ballasts is, of course, achieved with polyurethane. There is another story, safety, availability, acceptance. This we learn from our customers. Today, it's in why should you invest in those materials? It's not only a capex decision anymore, and not only a black and white finance decision, because nowadays track traffic is continually rising. There's less time for maintenance, mainly now at night and in the weekends. The staff is missing. They don't want to work at night or on the weekends anymore. And the ideal world for an operator would be a maintenance-free superstructure. Of course, we know that's not happening or not real life, but the materials who help you to get closer there are worth an investment. And what we hear from operators, that they say, okay, we really take this into consideration because we simply don't have the time for maintenance anymore. And that's why let me say, the investment decision is not only because of the price and performance of the materials anymore. And this is simply the reason why we're talking about this. We know polyurethane is working over such a long lifetime. The safety is not an issue. There is not too much deflection. There are no safety problems. And I talked about availability. We want to increase availability of your track because you have lower maintenance. And that's simply the reason why our heart is beating for those materials. As we know, okay, we can achieve the benefits our customers are searching. We get the acceptance in the laboratory, in the material tests, in the test tracks, and finally, of course, in the track. And that's why our passion comes for this material. And of course, not only for the material, our intention is really to make system railway more efficient and attractive. So we see us there really as a part of the system to develop railway and not only be a material supplier. A few words on the brands and the material, how it's working. You hopefully see a green line. That was Silodamp, orange is Silomer, and then you see the blue one, which is Silodyne. And when you look at the video, which should start hopefully, you see completely different behavior. Everything is polyurethane, but Silodamp is really a damper, normally not used in railway superstructure. Silomer is a, let me say, a combination between a spring and a damper, and Silodyne is really a spring, as you can see with the jumping ball. And Silodyne, of course, exact perfect material for mass spring system, and also mainly used there. And this we can achieve, by the way, because we are producing the materials on our own. We're not buying ready-made systems, so we really have the material parameters and properties in our hand. And when we talk about the usage of the material, we mainly talk about three areas. We have vibration isolation, superstructure protection, and noise reduction. And of course, the services, different customers, different needs. Vibration isolation is where we're coming from. That's how we grew strong. Superstructure protection has become the last years more and more important. As I said, life cycle cost topic, sustainability, increase of the lifetime of the track, one huge issue. And noise reduction, because of the urbanization, everything's getting closer together. We're talking about noise problems in countries where 10 years ago we wouldn't have even thought that it could be a problem there. The countries are developing, and the demands for, let me say, noise reduction are rising everywhere. And regarding the services, as I said, we not only want to be a material supplier, we really want to provide more than material data. Our intention is to understand the system, to participate in development projects with operators, universities, associations. That's why we're here today, by the way. And we spend efforts and money to understand the working principles of the complete system, that we create, let me say, the right solution. And again, that's why our passion from the material comes from, and the business. We really want to help to bring railway forward. Let's start with superstructure protection. This is exactly what you and we don't want to have. We don't want to have ballast deterioration. Ballast has become the weakest link, especially since we changed from wooden sleepers to concrete sleepers in many countries. We have high forces, high vertical forces of heavy trains, horizontal forces, and ballast has become the weakest link in this system. What we learn from our customers, water is the biggest enemy of a superstructure engineer, and you simply don't want to have ballast deterioration because of when ballast over the lifetime is getting wear, and you get a lot of problems with your drainage. Or you see here a good example of a transition zone. You see on the left side a ballasted track going onto the right side on a bridge where we also change from concrete sleepers to wooden sleepers, and you see those white spots. Perfect sign of a stiffness change. The ballast gets deteriorated, more wear in the complete system, and this will lead to a lot of maintenance in this area, and this can be avoided if you make here or use elastic materials to make, let me say here, a really smooth transition zone. Or also another example, what you don't want to have, you don't want to have broken sleepers, broken fixations, uneven ballast settlements lead to hollow sleepers. You see that on the top right picture. And then the white spots above the sleeper, when you know, okay, must be hollowness because of the dancing white ballast stones, simply things you don't want to have in your track. And some of you might ask, hey, does elastic material solve all these problems? Of course, not all of them, but we help to extend the lifetime of this system. And for those who are not infrastructure engineers, just a short picture, where are the products used? Below the rail pads, baseplate pads, below the sleeper, under sleeper pads, and below the ballast, normally under ballast mats. More details will follow from my colleague. And when we talk about superstructure protection, just shortly explained, what are we doing? We increase the bending line. We bring a defined elasticity into the track. We bear the load on more shoulders to get a better load distribution, and that helps to protect the ballast and by embedding it into our materials. So we still have stiff materials, but bring in a so-called elastoplastic behavior that you have an embedding of the stones, but still a stiffness to distribute the loading, and that's simply where we're good at. Let's talk or spend some words on vibration isolation, and not only superstructure protection. Railway tracks and living areas getting closer together. We see that worldwide urbanization gives us really a lot of challenges regarding protection of infrastructure or buildings. And we want to protect railway structures itself, tunnels, bridges, but of course also the buildings nearby, like hospitals, music halls, living areas. The requirements are simply rising there. And on one of my beginning slides, you have seen also a picture of building isolation. And as I said, if you're too late with the railway track, you can also wrap the building. And I can tell one example from New York. They built a huge luxury apartment with many levels there. The railway track was not isolated, so they isolated the building, because when you buy an apartment for millions of dollars, you don't want to hear everything shaking in your flat, or you don't want to have noise. And then, of course, you can also do the vibration isolation for the building and not only for the railway track. Because noise is an issue today. And I gave this example because it's an investment. They were able to bring the people closer to the track because they simply protect them, and then it's also an, let me say, investment decision. Short explanation, vibration isolation. What are we really doing? As I said in the beginning, perfect behavior of polyurethane. We simply reduce the natural frequency. What we're doing, we're shifting this line more to the right side. We bring down the frequency, and we do that, of course, with standardized products. But vibration isolation is always, let me say, project-wise calculated. We do customized solutions. We have a department which is only doing these calculations depending on the requirement. We select materials, we select dimensions, and because of these unique properties, the curve can be shifted to the required frequency, also to very low frequencies, depending on the form factor of the material. And the huge advantage is that with a low dynamic stiffness and this dynamic behavior, which normally means train is passing, load is coming into the track, we achieve these great vibration isolation properties. And depending on the requirement, we are offering different solutions, different products. Here I will skip over a bit or more quickly because my colleague will go into detail there. So really depending, okay, what line do you have? Is it urban transport, local transit, main line, high speed? Is it a ballasted track or slab track? What do you want to achieve? Vibration isolation, superstructure protection. And this simply then defines what kind of product do you need. And what would you like to spend, which benefit and performance you would like to get. And we will start with the sleeper pads. And here I will now hand over to my colleague, Stefan Loacker-Schöch. He will tell about these products. And as we said in the beginning, we will give some examples and case studies. And for undersleeper pads, we are happy that Mr. Knoll will do that from Austrian Federal Railways. So you won't see any references there, as anyway, Mr. Knoll will talk about it. So I hope that, Stefan, you can now take over.
Okay, I hope you still can see the screen. Also, hello from my side. Yeah, undersleeper pads, where are they located in the portfolio? So we're talking here about ballasted track. It's about vibration isolation or superstructure protection, but on undersleeper pads, the focus is clearly on superstructure protection. Undersleeper pad. You can see on the right, you can see where it's placed. So an undersleeper pad is an elastomer, which is placed below a concrete sleeper or mainly a concrete sleeper. Can also be used on a wooden sleeper and on a steel sleeper. And it does load distribution. So it will distribute the energy from the rail wheel interaction to the ground, and this by widening the bending line and therefore activating more sleepers. This will cause that each and every single sleeper has less pressure and less forces to handle, and this will result into less wear in the track. The second benefit of an elastomer is that you can increase the contact area on the ballast. So from regular 2 to 8%, if you have an unpadded sleeper, to a padded sleeper, you will increase from 2 to 8% to 15 to 35% with different stiffnesses on the elastomer. Below you can see a picture which was digitalized, and you can see the difference in contact. And nowadays we are also able to measure this in real track. So that's a measurement from real track where we could more or less cartograph the impact on a sleeper. And as you can see, those red peaks are not what we want to have, and those red peaks will cause ballast degradation. So here the pressure is too high, and if it's too high, the ballast will crack from time to time. What does it look like if you use an undersleeper pad, a polyurethane undersleeper pad, our most sold one with 7 millimeters? You will decrease these peaks. You will wider distribute on a single ballast stone. You see on the right quite good that from single peaks, very high peaks, you distribute the load on a wide area where where the contact pressure is less. Yeah, we also call it the Play-Doh principle. So the stone gets embedded, and it's in the Getzner USP. It's a less to plastic behavior. So we have elasticity and plasticity combined, and due to that, we are here leading when it comes to ballast contact pressure. So we can reduce here up to 80% the pressure on the single ballast stone. Another big topic is going on in the world. Climate change is known everywhere. and yeah, temperatures are rising. Therefore, also the tracks will have higher temperatures, and due to that, the elongation of the rails will cause some track faults. Of course, on the right, you see here a very, very extreme example, but what this undersleeper pad does as well is to avoid the lateral track faults. So we have an increased lateral track resistance due to the plasticity or elastoplastic behavior of the material. Now you could say we make everything up, and more or less that's a nice idea, but actually it's really also recommended from the International Railway Solution, the international recommendations how to use undersleeper pads, and they point out that if you have a track with a speed of 250 kilometers, mixed traffic, and a maximum load of 25 tons, you have a lifespan improvement of the track for 25 to 40 years. The track quality initially is 18% higher compared to standard track, and the track geometry degradation is reduced by 63%, resulting in a prolongation of the leveling, lining, and tamping cycles by a factor 2.75. So you can reduce your effort on the track by up to 2.7, by a factor by 2.75. This is written in the IRS. It's also stated in there when to use undersleeper pads, when not to use it, what are the boundaries, what is good for which situation, and yeah, you can find that it's open, yeah, to get from everyone. Next product of our portfolio are the underballast mats. They are one level lower, and we have here a quite famous example. It's the Gamsjäger in Munich. It's a concert hall, and here we added the underballast mat to do vibration isolation. And I think that the subway is around 20 to 30 meters away, and this you do not want to hear if you have a classical concert in such a hall. You don't want to hear if a subway is passing by. We did this installation in 1983. We did a regular check on it, and then the mats were removed the last time, 2012. They're still in there. They are more or less fully submerged with water. And what we recognized is on our material, we have had those values in the beginning, 1983. We had in 2000, we checked the values again of the material, so just a very, very slight change. And in 2012, we still have very, very similar values. And so after 29 years, the static body modulus is still in the original specification. And after 29 years, also the dynamic values are still inside the original specification. So quite a long time of our material in, and it proves more or less that our material does not degrade. It keeps its performance over a very, very, very long time. What is the underballast mat made for and used for? On one hand, it's on the lowest layer of a superstructure protection, mainly working with as vibration isolation. This was also the background of the underballast mat. So it's as you have quite high mass on top, you can achieve quite low eigenfrequencies. But what's kind of a newer approach is to use it for transition zones to make the stiffness of the track everywhere on the same level. So you want to have as homogeneous track as possible. And due to the fact that you install underballast mats on a bridge, you can decrease here the the stiffness increase of the bridge, and same approach is on tunnels where we have, for example, less ballast height. So when you have reduced ballast height, an underballast mat supports in keeping the stiffness over the track, on the track. Another product we sell in regard of elasticity, and also here main feature is superstructure protection. Of course, we are currently in development for a noise reducing one, but this is in the very, very early stage. We are doing here research to get here a product on the market which helps in noise reduction, but for superstructure protection, they are already in place. So especially if you have a highly stressed area, then the regular rail pads nowadays tracks get destroyed, and the polyurethane one are more resilient and lasts more or less forever. And the biggest project where we more or less sell our products are in narrow curves, so in mainline narrow curves, and in heavy haul applications where there is really, really high load on those regular rail pads. Another part, or on the slab track side, we have the mass spring systems. Of course, there are also sleeper boot, insertion pads, and baseplate pads, but this I don't want to cover into detail today. And because here it's really specific of the track design, what fits and what does not fit. But a mass spring system is often used to have really, really good vibration isolation. And based on this, there are different types of mass spring systems. So a full surface mass spring system can reach an eigenfrequency of 15 to 25 Hertz. The complexity is low in installation, but the attenuation performance is not really on very top level, already very good, but not on the highest level. To make that even better, you can go for stripe bearings, so stripe geometries. There you can further go down with the with the eigenfrequencies. And the best one is the spot bearing, where you can have the highest attenuation performance, but this installation is quite complex and also will, therefore cost more. Good. What do you more or less do? Due to that the size of the bearing is getting smaller, you reduce the dynamic force, the spring constant of the system. The mass more or less stays the same, and the eigenfrequency will go down. And why are we such systems really require a lot of engineering know-how. For example, in Stuttgart S21, there our products are installed. You need to do a feasibility study. You need to do NVH studies. Track designers you need to align with track designers. Then you need to select a certain material. This needs to be approved by the from governmental side. Then you need to do installation supervision, and later on you need to do measurements to see, yes, this installation is a successful one. And here Getzner Werkstoffe has more or less the whole portfolio. So we have those services in place, and we are happy to support here to make the vibration isolation at the highest level. A very good reference of that is the mass spring system of the Vienna Music Hall. It's a very well-known hall in the acoustics world, because it has one of the best acoustics for classical music. And this hall, there is a track, as you can see here on the left side, just 4 meters away. So this track 4 meters away would disturb the concert hall, and the acoustics will go down. And therefore, there was a premise that there shall not be any change in perception due to the emissions of the underground operation. And this we achieved by installing a siloline NE material in this certain size. They are every 2 meters you find these point bearings, and we reached here a natural frequency of 5.5 hertz, which is really outstanding and very good for this application. And we did here initial measurements in 2003, where we have the eigenfrequency at 5.4 hertz, and even 17 years later, there is no change, but the material still behaves very good, very well, and the customers are very satisfied due to that. Yeah, as said, no change in the natural frequency, no noticeable secondary noise in the concert halls caused by the metro, no noticeable vibrations, also no vibrations in the concert halls, and there are also no optical changes in the stylodyne bearings. So we went there where we remeasured them, and they still have the same shape and are looking very good. And I think we believe they will last forever there. Good. That was it, more or less, from the portfolio. Of course, as said before, the sleeper boot insertion pads and baseplate pads we don't want to cover, as it is highly depending on the track design, but they have more or less a similar effect than, for example, rail pads. And yeah. What can you achieve vibration mitigation wise? So rail pads, baseplate pads, you can achieve eigenfrequencies above 40 hertz. So here, not too much effect on if you want to avoid do vibration isolation. Under sleeper pads will go down to 30 hertz. Under ballast mats will reach eigenfrequencies above 15 hertz, and the mass spring systems will be around 5 to 6 hertz. In best case, around 5 hertz. Good. That was my part. I think, Thomas, I will give back to you and to explain the rolling stock application, where Getzner is also quite big.
Yeah, Stefan, thanks a lot. It would be great if you can just give me a short message if it already changed. Can you see the picture of the rolling stock?
Yeah, looks good.
Perfect. Then I will continue, because maybe we have some people from rolling stock also joining. We talked a lot about superstructure protection, but our materials are also used in the rolling stock industry. As you can see on this picture, a train from Hitachi in the UK, and you see the floor panel and an orange stripe coming out of it below. So that's quite normal to do strip protection below the floor panels. There's, of course, as I said in the beginning, the vibration isolation properties are great. Also, the reduction of the floor head can be reduced compared with standard materials like rubber bearings. You have the same or even a better performance. Noise level in the rail car is going down, and also tolerance compensations during installation can be covered. You see here 2 pictures or examples. The one on the left top is from India, Delhi Metro, where they just bonded the material on the raw rail car wagon, and then normally the filling material goes in between, and the floor panel is bonded on the top, because when you screw it, you make a sound bridge. So you normally do a bonding, and it's really a box-in-box system, because this you need to have. Otherwise, you don't achieve the performance you would like to have. On the right bottom, you see Alstom workshop. Here they bonded the strips on the floor panel and then lifted into the rail car. So it's simply depending on the production process you have. Advantage for the operator, decreased life cycle costs due to less maintenance of the floor panel, because the strip below is not the weakest link. And it's a lightweight material, which, of course, everyone wants to have lightweight materials. If you want to make your train lighter, which finally also needs or results into lower energy consumption over the whole lifetime. So also huge advantage there. Some examples just mentioned, you see different train types, and depending on the performance, of course, the thickness of the material is different. And finally, when you can achieve a higher riding comfort because of less noise and vibration in the rail car, you achieve a high acceptance of the passengers. People more likely use trains, and of course also the availability of the trains is better when you don't need to go for maintenance. So it all in all again leads to more acceptance of the railway. And finally, I want to spend 2 slides on sustainability, because that's a topic which, let me say, I just heard in the last weeks that plant grows very fast. Of course, not everywhere in the world, but especially in Europe, I believe. And you may ask yourself, how can it be sustainable to bring in, and my heart is bleeding when I say that, to bring in plastic into railway, because polyurethane is raw oil-based material. And everyone may say, hey, cannot be sustainable. When you look at the product itself, you may write, because when you just look at the CO2 footprint compared with the granulated rubber, of course, polyurethane is more worse, simply. But when you look at the total system, and here again, I'm very happy that Austrian Federal Railways gave that study or that order to Technical University of Graz to do this study. And they looked, okay, what is the most sustainable superstructure? And they compared different sleepers, wooden sleepers, concrete sleepers, and padded concrete sleepers. And they found out, okay, when you look at the whole lifetime, and now everyone tells a story about sustainability, and this is simply ours. When you look from it cradle to the grave, which I believe is really the most important one, and you look at the total system, you see, okay, you save really maintenance for tamping, for grinding. If you not just only send the guys out to do it, you really look at the wear in the superstructure and then react, and then you save energy, a lot of energy, and that leads to the result. University of Graz found out that concrete padded sleepers on the long side are the most sustainable superstructure. And it's a reduction of the CO2 footprint in the system. And this is what, let me say, really is important for us, that we see, okay, we're on the right path, and not only looking, let me say, on material CO2 footprint. And I also want to speak or spend a few words on recycling, because there's an image in the market, polyurethane cannot be recycled. That's simply not true. We found a way to do that. We're happy that we have resources, and our owners give us the money to do that. We will launch next year the first 100% polyurethane recycled granulate products. We do that on our own. And we also found a way to do chemical recycling, that we really can produce, let me say, new raw materials out of it. And to achieve this is sustainable requirement from the market, and be, let me say, or also green products is maybe too high, but really to use the waste and not to throw it again, and simply do recycling. And these are my final words. I say thank you very much for your attention. I see that the number of participants is rising, and I expect they are all waiting for Mr. Knoll and his interesting presentation from Austrian Federal Railways. Stefan and I say thank you for your participation. I hope it was interesting. I put our contacts into the chat. Here they are again too. So if you would like to deepen the discussion, go more into details, we are happy to do so. Just contact us, give us a note, and we can forward you to the right people. And I hope it was interesting for you to see this, to get this overview. And yeah, back to Madeleine and to Mr. Knoll.
Great. Thank you, Stefan and Thomas. That was a great presentation. So we are not over yet. We are now going on to Bernhard Knoll, who is the Vice President of the UEEIV, as well as being the head of Superstructures for the Austrian Federal Railway. And so he will talk to us about his experiences with the Getzner products. So over to you, Bernhard.
Thank you very much, Maddie, for the kind introduction. I hope everyone can hear me. I share my presentation soon. Well, good evening or good late afternoon to every one of you. It's a pleasure for me sharing our experience, my experience, the experience of the Austrian Federal Railways, especially on the use of undersleeper pads. I think for the last 20 years already, we have experience with this, and I want to share this knowledge with you. First, let me give you, for introduction, a short overview on our small country. You know, Austria is not really the biggest country in the world, around 83,000 square kilometers with 9 provinces, and around 20% of the people are living in Vienna, our great capital. And even in this small country, we have more or less 9,700 kilometers of tracks. If you compare the line lengths, it's of course not so much. It's around 4,800 kilometer line lengths. We operate trains, and 1,250 of them are dedicated high-speed lines. We have a high dense of switches and crossings, around 13,500 S&C. Which cause, of course, a lot of problems sometimes. We have 28,000 signals, around 6,000 bridges and viaducts, around 250 tunnels now already in operation, 3,500 railway crossings, and more than 1,000 stations. So this is for me to you to give you an impression of our network. And now let's go a little bit more in the detail. How it all began. In 1989, I found the first publication or first tests at SNCF laboratory has taken place using concrete cubes covered with polyurethane. Even 1 year later, in 1990, the first project with undersleeper pads was realized by a Getzner company at Metro Oslo. Then there was a few years of delay in 1994 to 1996. Austria and Germany together started their first test trials in track. And I remember in one paper in 1997, the first big project, Öresund, was also realized by Getzner company with undersleeper pads. In the same year, Austria took together with some partner universities and of course with Getzner company, we investigated to do more research work on undersleeper pads with the aim, the reduction of vibrations, reduction of corrugation, especially in tight curves, and the optimization of track position stability was the aim to find out in this research projects. And in the same time period, more or less, also UIC has started launched a very big project, around 4 years of project time from 2003 to 2007, with a lot of countries participating, giving their state-of-the-art knowledge at that time to bring you to give information on the performance of these undersleeper pads. It resulted in a more or less summarizing report which was published in the years 2007 until 2009. There were almost 4 editions. The paper was called Under Sleeper Pads, and I think it's still available on the net. More or less, the latest version of this UIC summarizing report has been transferred to a new IRS, an International Railway Solution standard from UIC 17713-1, which is you can buy from the UIC homepage, and it's called Railway Applications Track and Structure Under Sleeper Pads Recommendations for Use. So a big project took place to transfer the demands of a Euro norm on under sleeper pad products to give a hint or a recommendation for use this kind of product in the railway field. And from my personal view, up to now, under sleeper pads are a story of success. Let's step shortly back to this UIC project. You see, it was a very huge project, taking into account the state of the art in this year, 2004 to 2007, doing some theoretical investigation on the track dynamics, the track settlement, the stresses within sleepers. Acoustics and vibration was a big topic. Also, the standardization of the material. Last but not least, some laboratory measurements on these static and dynamic stiffnesses of these material products. The famous vibro shear test from SNCF was defined as a good method to demonstrate the performance of under sleeper pads in track after a lot of runs over the track. And finally, also some test track measurements were presented there in various countries, Austria, Switzerland, Germany, and a lot of other countries gave their track measurement results in this document you see here on the screen. And the benefit which was observed from these under sleeper pads was described in this final report, that it is a compensation for localized differences in track stiffness, e.g. transitions between different construction types, between embankment and bridges, and especially at level crossings. It could find out that the reduction of high frequency vibrations and especially structure-borne noise, USB being used as an alternative to under ballast mats in the frequency range above 40 to 50 Hertz. And last but not least, a very good benefit to reduce the reduction on-track machine maintenance. So it could be found out that track geometry is much more stable over a longer period of time, and therefore a longer interval between tamping is possible. So those were the 3 observed benefits of these investigations at that years. Of course, with not so much experience in the track side, in the field, but it gave us, as in Austria, the possibility to do some more investigation on this topic. Now, when we see, when we do some new track laying, how it starts, more or less we start with laying some rails and sleepers. We put in the ballast in the track, then there come the big yellow machines for the tamping. We need some sort of surveying, and finally, hopefully, we are running safely our trains on these tracks. But when we do this, by the time, what can come of it in the course of time, we could get problems with our rail surface. We may confronted with problems with our rail pads. We see the imprint of the rail foot into especially concrete sleepers if these rail pads do not work properly anymore. We see some fine material coming from the subsoil being pumped into the ballast bed. The destruction of the ballast may cause these wet spots, we call it. Finally, track geometry, not only in the alignment, but also in the vertical plane can become quite difficult by the time. More or less, as we have already seen a picture, the destruction of the ballast stones because of the high frequency dynamic loads coming, vertical loads, destroying the weak ballast stones, starting to get some corrugation on the rails. This will probably lead sometimes in a bad, yeah, in the bending, in a too high bending of the sleepers, which may cause cracks. We got this kind of steep corrugations, especially in very narrow curves. Yeah, and last but not least, we have to rehabilitate probably also the ballast, not only the ballast, also underneath the subsoil, do some subsoil rehabilitation, and this more or less is the typical typical degradation of a track by the time, which namely is affected mostly because of one simple problem, and this is the elasticity in the track. So when you conduct causal research, you very often and very quickly come to an essential parameter in the track system, which is the main reason for many subsequent development. It's the missing elasticity in the track. So elasticity is decisive for the development of the later track geometry position, but also for the development of the superstructure components itself, especially in terms of wear and overstressing. As we have already seen from our colleagues from Getzner, to improve load distribution and thus minimize ballast and superstructure stresses, it is possible to insert elastic elements at various points in the track body. In the top area, we have between the sleeper and the bearer or sleeper, we are able to put elastic rail pads in between. Directly under the sleeper, we can put this so-called undersleeper pads, and at the top of the formation layer, finally under ballast mats. Those are three elastic elements we can put to our track to improve elasticity and hopefully to prevent our track from deterioration and getting failures we have seen in the slides before. So let me start what is USP itself. USP is the term used to describe elastic layers that are attached to the bottom of the concrete sleeper. This has more or less a positive effect on the whole dynamic behavior of the track in the ballast bed, and of course increases the overall track position quality. So the materials which are used are usually from polyurethane, as the colleagues from Getzner have already demonstrated before, but it can also be from rubber material, natural or synthetic rubber. It might be from ethylene vinyl acetate, the very famous EVA material we use, for example, in wooden sleepers. So there's a number of elastic materials which can be used as a elastic layer on the bottom of the sleeper. The application is more or less depending on the material side. So we have experienced, we started first with some kind of coating by spraying or painting this elastic material to the bottom of the sleeper. Then in the next phase, because this coating was probably not so proper, we tried to glue it, especially on S&C, on turnouts. First, we have had to glue this under sleeper pads to the sleeper. The next step was to insert it directly into the fresh concrete during the production phase. And sometimes, depending on the material, like from Getzner, we have this special interlocking layer, which is a wire mesh, but it can also be a geomembrane or fine grained gravel or some extruded knobs you can put to to the material, special to urethane, to get a good contact to the sleeper, to the concrete sleeper itself. So there are lots of products on the market which can be used for under sleeper pads. When we are looking for specification, what are minimum requirements in the railway field, then I can introduce to you the Euronorm 16730, which deals with concrete sleepers and bearers with under sleeper pads. And this IRS standard I've already mentioned, under sleeper pads recommendation for use, where only infrastructure manager gave input about their experience and the recommendation for use of this kind of material for the various field of applications. If you only want, if there's a special need for reducing ground-bound vibration, or if it is a special use for preventing a ballast from damage. When we look to this Euronorm 16730, you find there requirements for the qualification and routine tests, which should be performed for this kind of USP. The data which the supplier or manufacturer should last but not least send to the client. The rules for the use of sleepers and bearers with USB. There is a chapter on quality control, and last but not least on marking, leveling, and packaging of these materials. So even if you have not so much experience, I think when you have a look to this Euronorm and you ask your supplier for fulfilling this Euronorm, I think you get in principle a good product. In the annexes for the experts, you will find all the test procedures which need to be performed, from stiffness measurements, fatigue behavior tests, and in bond strengths, pull-out tests, effects, even on effects of environmental conditions. There are some test procedures described. So I think a good Euronorm, which is then additionally interpreted with a recommendation for use by this infrastructure manager in this special IRS 7713-1. Well, in this recommendation for use of under sleeper pads, there is a distinction between different under sleeper pads types. There's a distinction between stiff, medium, soft, and very soft under sleeper pads. It can be clarified or classified by the so-called static bending modulus. The lower the value, the softer the pad. And in this recommendation for use, you find also this graph below on this graph, which kind of type is suggested to be put in the track. So if you're talking about reduction of ground-bound vibration, there's a tendency more to very soft or soft rail pads. If you only want to prevent the ballast from damage, then you're probably here somewhere in the medium and stiff area. So those are two tables you will also find in this recommendation for use railway solution. When we're talking about some economic evaluation of this USP, the colleagues from Getzner have also mentioned it before that in 2012, Technical University of Graz and Professor Veit has launched an economic evaluation. Of course, it's now 10 years old, but I think it's still valid. It is a classical LCC calculation where the total costs are investigated, and those LCC methodology includes more or less the costs of the initial construction, then the ongoing maintenance costs, all the operational hindrances, and last but not least, also the disposal costs at the end of the service life of the asset. And one of the results, there are of course a little bit more in this paper, when you look to the internal rate of return for under sleeper pads, even with a very conservative approach. And you see that this paper is 10 years old. So now we have a much more higher knowledge on this and much more numbers. But even at that time, with very conservative approach, the internal rate of return for USB is here shown for a classical curve with a radius of 500 meter. So it shows, from my point of view, a very high economic efficiency with a rate of more than 5 up to 10%. You see on the x-axis the transport volume in gross tons per day and track, and here the internal rate of return. So when you calculate with 5%, which is, I think, a regular value you calculate for an investment, you see that there's almost, for sleeper with under sleeper pads, no reason not to implement it in a track, even if there's a variation in the costs of these under sleeper pads additional to the sleeper costs by 30% up to 50%. It is still very high. The rate of return is still very high, and therefore is a recommendation that actually every concrete sleeper should be equipped with under sleeper pads independently from the transport volume on the line. So this is the result of the calculation. Of course, with the last increase of costs in the world, the graph will probably change a little bit, but I think from the principle, it's still valid and right what is said here. Now let's go from the more theoretical part to the real experience in the field. I've already mentioned that we did a lot of investigations in the area between 1997 and 2007. We did some equipment on the track, or we equipped some tracks with under sleeper pads in our network. We have chosen 3 different kind of application. Under sleeper pads which fully covered the whole bottom of the sleeper. We also tried a solution which is where it is only partly covered, so only directly under the rails, so 2 smaller parts of under sleeper pads. And we also did some trials with conical shaped under sleeper pads. When you look to the measurement runs of the trains, you see more or less not really a major difference in the performance. So we are very happy with the material, how it works. We still use fully covered under sleeper pads in our track. So we discovered or investigated the performance in track mostly with our track recording car, our EM 250, which give us the so-called mean value from the standard deviation longitudinal level. And this value is the one where we can get the feedback on the performance of the track. 2 or 3 years ago, I tried to sum up all these test trials, and one of these 7 I have marked here. The last one from in the Salzburg area between Vienna and Salzburg, which was installed in 2004, and with a tonnage of more than 400 million cross tons. At the time it has been investigated. I will show you now the final results. So it is a track with 28 million gross tons per year. We have a track with a radius between 400 and 600 meters track. So it is a very curved line, very much left hand and right hand turns following up. We have the typical concrete sleeper with under sleeper pads. The speed we are running there is 95 kilometers an hour, and we use the 60 kilo rail profile 61. And we have a soft rail pad. Since 2007, we use on concrete sleeper only soft rail pads with a static stiffness of maximum 100 kilonewton per millimeter. so quite soft rail pad. Plus, in this case, we had 3 different sections. The first and the third section were equipped with no undersleeper pads. This K1 is the type of the sleeper we use, so a 19A is a special concrete sleeper type. And here you see the range or the length of the net where it has been implemented. So 1.5, more or less 1.5 kilometer without undersleeper pads, then more than 3.5 kilometers with undersleeper pads, and then 1.5 kilometer without. And here I show you the results of in the time period from 2004 until 2018. The left-hand graph is our typical Natas measuring strip. Here you see it's a combination of all the data we measure with a measurement car. But here in the gray line, you see the so-called curvature of the track. So you see a lot of curves, left and right-hand curves. And here you see the cant of the track. So it's really not a straight line. It's really very tight curves in a range of 400 to 600 meters. And here you see also the area where the sleeper pads have been implemented. And before and after there is the track without the sleeper pads. And every measurement run with our track recording car, and we do it between 2 and 4 times a year. At this category of line, you will find here a dot. The orange and the red ones are the one without undersleeper pads, and the blue one is the section with undersleeper pads. It is the mean value of the standard deviation longitudinal level over the whole section, and after every measurement run, you got this dot, and there you can see how the values of the standard deviation longitudinal level deteriorated. And you see first, we have installed it in 2004. Here some around 2006, the first tamping action took place on the 2 areas without undersleeper pads. The next tamping shift was around 2010, somewhere in September. And the next tamping was necessary in 2014. So we see in those areas where there were no undersleeper pads installed, we have a classical tamping cycle of around 4 years. Around 1.5 millimeters standard deviation was our intervention level for tamping, and those were the classical cycle of a tamping action in this area. And when we now look to the more or less 3 kilometers of track with undersleeper pads, we see that the first tamping was needed in 2009, and the second one more or less in 2015. I think in this area something happened. I think there was a short section was tamped. That's why there's a small decrease of the values, but the tendency, I think, is very clear that the tamping cycle were increased in this area with undersleeper pads, even with narrow curves, as you can see here, is around 6 years. So we could increase it by a very high factor. And even if you see the inclination of this curve, the degradation is very flat. So you would see here that you could have last this track probably another 3 or 4 years when you say that your intervention level is 1.5 millimeter. So you see really a great performance. In this same performance, I could demonstrate you on all the other 6 examples I've showed you before, but I think for today, 1 example is enough. When we look to the application, I think since 2007 now, we equip all our tracks where we implement concrete sleepers and where we have more than 30,000 cross tons per day and track with undersleeper pads. So I told you before that from the economical basis, actually there is no limit, no limit for the loading of the track for implementing the sleeper pads. But nevertheless, for our railway, we said it's not necessary. We have actually good ballast, but when you run with more than 30,000 cross tons a day with our ballast conditions and our ballast quality, it makes sense to equip all concrete sleepers with under sleeper pads, and that means around 200,000 pieces per year we put in the track with under sleeper pads. We also do it since 2007 on all our SNCs where we have concrete sleepers or concrete bearers, and this is around 150 to 250 bearers per year, 150 and 250 turnouts per year we implement in our track. So here you see on the left-hand graph the increase of the concrete sleepers with USB starting in more or less 2006, 2007, and reaches the top very quick. And when you count it together, we have totally installed now around almost 2,000 kilometers of tracks with under sleeper pads, with concrete sleepers, and around 1,800 SNC. So I think a huge amount of numbers, and I think we have a lot of feedback from it, and we are quite happy with it. Especially also in turnouts. You know, in turnouts we have the problem with the inclination and the bending, which takes place with every train running over the track, the bending of the concrete, and therefore we also found a good solution by implementing under sleeper pads. This graph you see without under sleeper pads. Here you can see the cant and the twist shown on this graph, especially in the frog area here. And actually from the beginning of the turnout until the end, you see that there's a starting, the cant is getting more and more, and even also the twist is performing worse. And with under sleeper pads, you got more or less a homogeneous performance of the track in relation to the track geometry. And the reason is we did some investigation on the finite element method calculation where we looked how the settlement takes place in these turnouts when you run in the main line or in the diverging line. And with this finite element calculation, we found out which different kind of elasticities you need in the whole turnout to get the best performance. And nevertheless, the reduction of the ballast bed stresses and the better elasticity leads to a better track geometry, of course, reduced maintenance costs, actions and costs, of course. And we found out that even in turnouts, USB can reduce the settlement and gives a better track durability. And how we do it, I show you on this simple graph. So we are actually using 3 different elasticities of our under sleeper pads throughout the turnout. So you see the areas where we use a little bit more stiff under sleeper pads, and then you see even in the length of the bearer on different areas we use more or less stiff materials with this special equipment we got a very homogeneous settlement of the whole turnout, and we can prevent the problems with inclination, with bending, with twisting throughout a concrete turnout. Well, our first initial idea when we started investigating on under sleeper pads was to prevent the ballast from damage. In 2001, Austria has started to run the first trains with high speed. When I say high speed, I have to be honest, it's only 200 kilometers an hour, but this was in former times high speed for our network, where before 160 was our highest speed. And now we changed in 2001 on certain sections of the Western Line to 200 kilometers an hour. And very quickly we found out that the classical superstructure with concrete sleepers damaged our ballast. Obviously, our ballast quality was not the best. So we found out that this insufficient elasticity in the superstructure combined with stiff subgrade conditions. In the years 2000, we also had a very stiff subgrade implemented in new lines, something we would not do again anymore. Now it is much more weak. It's no more so stiff as it was 20 years ago. And this has more or less led to a very high sleeper ballast forces and premature ballast wear. We got fine ballast abrasion, and those were the so-called white spots, which we have already also seen before. And when you got this kind of white spots, when fine grain sizes fill all the space, the empty room between the ballast grains, you have a problem with the water impermeable ballast abrasion. Then you got this so-called wet spots. Water cannot flow away. Wet spots occur. You got a loss in the stable ballast compaction. You got a very quick deterioration of the track geometry. You have stress-induced transverse cracks in the sleeper. The tapping intervals getting always shorter and shorter, and nevertheless the lifespan of the track decreases. So we were confronted with this problem, and we thought that under sleeper pads would probably solve this problem. And as we have already seen before, it is the case that conventional concrete sleeper without USB is only in contact with 5 to 6% with the ballast. That means small area and high forces get more damage than if you use USBs with a much more significantly increased contact area where the stones can press into this elastic layer. And as we have already heard, around 25% more area where you can distribute the forces prevents the ballast from damage. The so-called force pass, the forces which going from one stone to the other, coming in the vertical direction, much better distributed, are more uniform, even if dynamic traffic loads are coming from the surface. And yeah, this was our investigation on that. The next thing is what we wanted to achieve is a much better track geometry. So we see that on existing lines, we have sometimes the problem that these fine grains soils and that we have inadequate drainage by the time. But when you use undersleeper pads, you could increase elasticity in the track. Even the distribution of the wheel load over the longer track lengths is possible. So then, and of course, the greater rail deflection leads to lower stresses in the sleeper and the ballast, but increases the stresses in the rails. So this is something you have to take into account. Even that you have probably higher vertical acceleration, but you do something good for the ballast and the sleeper. Here I can show you from our southern route from Vienna, the direction Graz and Klagenfurt, measuring from the measurement car. You see the measurement strip of the longitudinal level between, this is a section of around 3 kilometers of track. And here you see an area where undersleeper pads has been installed. It's also a very curved line. And every color you see here is a run with the measurement car. So we did here 5 runs in the period between November 2005 up to June 2007. And you could see that in this area where the sleeper pads have been installed, there's more or less no change in the track geometry. You have still a very good standard deviation longitudinal level. The deterioration rate per year is quite low. If you compare it to the adjacent sections where the performance becomes poor and poor by the time. So, as I have already said, lower forces and settlements in the subgrade, longer tamping intervals, and the softer the rail bed, the longer the lower the long-term subgrade settlements are the one experience we have faced. And we think that this gave us really a much better track geometry and helps us to increase our performance. This picture is also something we have already seen. Also, in our network, we have very narrow curves, so we are not in the lucky situation to have a lot of straight lines where you can run with high speed. We have a lot of mountainous areas where we have very narrow curves. And the aim with under sleeper pads was also in combination with concrete sleepers and stiff under sleeper pads. We have already seen, as without under sleeper pads and stiff rail pads, we saw that this kind of concrete sleepers tend to develop very quick corrugation. And we found out that by implementing under sleeper pads, this corrugation becomes not so quick anymore. It takes much more longer time for the development, and therefore you can prevent this early wear of the rail pads, which occur in very narrow curves due to this corrugation. You can increase the rail grinding cycles. Even you can reduce these high stresses in the rails you are facing in corrugated tracks on the low rail. And of course, the high noise emission for the people living around can also be avoided or enlarged by using under sleeper pads. And so a good colleague of us, Mr. Florian Auer, did in his master thesis a lot of investigation on the combination of various soft materials from rail pads down to under sleeper pads. And by selecting a proper superstructure, I think, which looks like head-hardened 60-kilo rails combined with soft rail pads with a good fastening system, with probably a little bit greater holding downforce and adequate USB, you can increase service life even in tracks with very narrow curves. Another graph, we also tried to find out if it's possible to reduce the ballast thickness by using under sleeper pads. So we equipped a section of line with only 45 centimeters of ballast bed thickness and followed by 55 centimeter ballast of thickness. When I talk about 45 and 55, I have to tell you that we measure the depth or the thickness of the ballast starting of the top of the sleeper down to the formation layer. Most of the railways measure from the bottom down to the formation layer. We calculate this thickness from the top of the ballast of the sleeper or from the bottom of the rail foot. And as you can see here on this graph, you see almost no difference in the performance. So we could find out that if you have a very good subgrade condition, that means if you have underneath your ballasted track some kind of bituminous supporting layers or very good other kind of layers, then a reduction of the ballast bed thickness by up to 10 centimeter is possible without early track deterioration. And this may save around half a ton of ballast per meter track. So if someone wants to spare some money, it works, probably works. This was our experience on one special line. We investigated it. And another thing which is heavily discussed in a lot of infrastructure managers, we found out that it is possible to increase the lateral track stability by using under sleeper pads up to 10%. When you do the classic measurement with so-called single sleeper push tests, which is the standard in USC, but also in a lot of countries, to measure the so-called lateral track resistance, or better to say, the so-called sleeper ballast resistance of the track. We found out that if you equip sleepers with under sleeper pellets, you may get or increase this lateral track resistance. I have shown you here 7 measurements in 7 different areas. The one is the so-called lateral drag resistance at the 2-meter lateral displacement. This is the maximum value we have measured in Newton per millimeter. And you see the first example was a concrete sleeper with under sleeper pads, but in an unconsolidated situation. That means directly after track laying with tamping and stabilizing, but with no trains having run on this track. And the same was done with example number 2 and 3, but here there were no USP mounted. So you can see here a difference of 10, probably 20% higher performance of under sleeper pads with rail pads, because we think because of the better possibility to imprint in this elastic layer, like in a wooden sleeper, you got better resistance in the lateral direction by this kind of under sleeper pads. Of course, you have to take care which kind of under sleeper pads you take, very weak one or soft one or very stiff one. It will also be depending on the material you use, if it is polyurethane, if it is rubber, or if it is EVA. Probably you will get different results. But the tendency, I think, everywhere, also in Germany and in Switzerland, the tendency is more or less clear that under sleeper pads do not decrease the track stability, it increases it by a certain amount. And I would suggest we can clearly say it's up to 10% anyway. The next goals we want to achieve with under sleeper pads was the reduction of noise and vibrations. And therefore, I can tell you, up to now, we do not have so many tracks where there was a need to reduce vibrations or demands from any authority to implement special equipment with under sleeper pads with against noise and vibrations. So our experience is not so big, and that's why I want to highlight to you the results, the big results coming from this UIC project. And the results there was that it is possible to reduce vibrations and structure-borne noise by up to 30% by using USB. The reduction occurs from a frequency of above 50 Hertz. So it only gives you good results if you have frequencies higher than 50 Hertz. The insertion loss is not too bad. It's around 8 to 15 decibel. And the resonance frequency is in an area of 25 to 40 Hertz. So the resonant frequency changes, of course, with the modulus of the subgrade reaction of the USB. And it was also found out that the direct dependence between modulus of subgrade reaction and structure-borne noise reduction could not be determined at this time when it was investigated. So one thing is still a little bit open and not so many measurements exists. The tracks with under sleeper pads presumable have a minimally higher value for primary airborne noise than probably standard tracks. But you know, primary airborne noise is always also a product of the rail pad you use. So the combination of rail pad, under sleeper pad, and probably under ballast mat in combination has a big impact on the final airborne noise, and therefore it's always difficult to say who is responsible for airborne noise. But something we can definitely say that the primary airborne noise cannot be reduced by implementing USB. It is more or less equal or not worse, but it can, or only a little bit higher, but it cannot decrease like noise and vibrations. There you are really up to 30%, which can be achieved. Yeah. Let me summarize. I think I now had a lot of time to present to you. After more than 20 years of experience in this application of USB in Austria, I can really state with conviction that USB has raised track and SNC construction to a new level. It is by far the greatest innovation of the last 50 years in track, I would say. because the main advantages are so huge. It's not only the better load distribution because of the better contact, the increase of the contact areas. It is the protection of the ballast bed. It is the improvement of the track geometry quality. It is the extension of tamping cycles, which gives you a huge amount on cost reduction. There also the possibility of reducing ballast bed thickness, the reduction of corrugation in narrow curves, and also the reduction of structure-borne noise and vibration around 30%, together with also with a cost-effective alternative to under ballast mats. So sometimes when the reduction which is needed is so big that only under ballast mats can achieve your goals, then probably these under sleeper pads can also be a cost-effective alternative to these mats. And I think those advantages are so huge that this is the best and greatest innovation of the last 50 years in tracks. So nothing more to say. I say thank you for listening, and I'm waiting for your question if you have some. Thank you very much.
Great. Thank you, Bernhard. That was brilliant. Appreciate we have run over a bit, but I thought Bernhard's insights was very interesting, and I think would be interesting to other people as well. So I'm glad everyone was able to stay on. We will start taking any questions. I think there are some in the chat, and then also if anyone wants to raise their hand, they can, and Charlotte will be able to unmute you and you can ask yourself. But yes, so thanks again to our speakers, Thomas, Stefan and Bernhard. That was brilliant to get a full insight into what all these elastic solutions can do to our railway. Like, even what was interesting for me was in the switch and the turnout, you are able to use different thicknesses depending on your kind of need, which I think is very cool. Yeah, and so thank you very much for all your insights. So we'll start. We have one from a question from a guest who has asked, which kind of USP, stiff, medium or soft, according to the IRS classification, are you using to alleviate corrugation problems in curves? What is your experience in corrugation mitigation? Thanks in advance. I'm guessing this is for you, Bernhard, but
yeah,
Thomas and Stefan
I can immediately ask you. Also, we always use stiff rail pads. So the stiffest under sleeper pads we can get. This is the classical SLB 3007, the 7 mm thick with a statical stiffness of 0.3 mm. The stiff rail pad we use in the track, not only to prevent the ballast from damage, but also in narrow curves to prevent this corrugation or to enlarge this corrugation development. But you have to take into account that we always use soft rail pads in combination. So soft rail pads and hard or more or less stiff under sleeper pads. This is the best combination.
Cool. So why is that, Bernhard, to have this combination, to have the stiff? Is it better, you found, to have stiffer foundation and more rail movement?
We found out that even if the under sleeper pad gets too weak, you got more deflection and it does not give you a better performance. So we found out that even with a more or less stiff rail pad, you can achieve more or less all the problems or solve all the problems you have, because you also have to take into account when you have rail pads, you have under sleeper pads and under ballast mat, you have a 3-mass swinging, and this is more difficult to handle. I think I would hand over to the colleagues from Getzner to explain.
Yeah, they're nodding a lot.
What can happen if 3 masses are moving in the wrong direction?
Yeah, Thomas, Stefan, do you have something to add, maybe?
Maybe from Thomas, if okay for you to add here. So in our experience, what you see is if you give the rail on very top the freedom slightly to move, that's sufficient that this corrugation will not happen. This you can achieve by a softer rail pad, but you don't want the track to be destabilized. So for stable or really good track rigidness, you go for a stiff one. So combination of this leads to a stable track, but gives on top the freedom that the rail can slightly move in case of harder impact.
And what we of course see is that the experience from Austrian Federal Railways over these long years, they started to look at the total system. We have other countries who say, okay, let's use the undersleeper pad, fine. And later on, they do the same investigations like you said, Mr. Knoll. They suddenly start to think about the wheel pad in combination. Then maybe later on the under ballast mat. And I think that's why it is great to have your experiences here, looking at the total system and what are the changes. Like you said, soft in combination with stiff gives the best results. Others normally just start with one part and only consider one part of the system, and it's the combination you have to look at simply.
I would also give you the recommendation for some in the audience who has not so much experience. I can only say, try it yourself. You have to try it yourself. Do a first test track, equip it, and then have a look on your measuring data. And the more you can convince in your company, in your infrastructure manager or your track masters outside, you have to do your own experience and see the good things. It's not good only to talk about or hear it from somewhere. You have to make your own experience.
Okay, thank you all for your insights. If anyone has any other questions, feel free to add. I will look through and just check. But I think, Thomas, you have answered some already, and you've put your contact in the chat so people can speak to you directly.
I try to be active, yes.
No, that's brilliant. Thank you. And yes, so this whole presentation will be shared online on the UEEIV website, so you're able to watch it again if you missed anything, and share it with your colleagues. But if there are no further questions, I will close this meeting. Thank you everyone for joining, and also again thank you to our speakers. That was brilliant. Cool.
You're welcome.
And see you next time for our next railway talk. There will be more details showing. But yes, thank you. Cool.
Bye-bye.
Thank you, everyone.
See you.
Bye.
Thanks for participation.
Bye-bye.
Thank you. Bye.